Hey students, this is Mr. Heinrich, and we are looking at Newton's laws. We are finally done with our kinematics unit. And in kinematics, we talked all about acceleration, and we started discussing the direction of it and what it could do. It could either slow down a positive moving velocity if you had a negative acceleration, or if you had a negative velocity, if you had a positive acceleration, it could slow that system down. Or the more obvious, if you have a positive velocity and a positive acceleration, it speeds it up in the positive direction. But where does acceleration come from, right? That's the big question. Where do we get acceleration from? And it comes from force. It comes from forces. And we have a intuitive understanding of what that is and what they are, but we need to get to the bottom of what force really is and how we can start to understand some laws that help us deal with these forces. And yeah, I'm talking about Newton's laws. Newton's laws, which help us understand force, and force is the cause of any acceleration, okay? So let's get to the first law. Let's just jump right in. Actually, you know what? I always forget to do this. Let's do this first. What is the simplest definition of a force? Definition of force. It's nothing more than a push or a pull. I don't care if you're talking about atomic forces, if you're talking about you and your brother or sister fighting, right? Any force is just a push or a pull. That's all it is. So let's get right into that first law. That first law, I bet you guys already know it. Simply stated, an object in a state of motion will remain in that state of motion unless acted upon by an unbalanced force. Now, you're used to hearing external force. It's not wrong to say external force, but I like to say unbalanced force. So an object in a state of motion will remain in that state of motion unless acted upon by an unbalanced force. Which leads us to talk about what is a state of motion? State of motion, right? There's a lot of states of motion. But when I say state of motion in this statement, I mean one of two parameters or one of two things. Okay, so under here I'll put in parentheses state of motion. Well, right now you are in a state of motion. You might not feel like it, but to say that you're not in motion is a state of motion, believe it or not. So if you are at rest, then that is a state of motion. It's a state of not having motion, but it's still a state of motion. So rest is one of them. What's the other one? The other one would be moving at a constant velocity. So state of motion refers to either rest or constant velocity. Now let's prove it. You would stay sitting in that chair taking these notes until you decide to create an unbalanced force, probably from your quadriceps, right? Your leg muscles that make you stand up. You would stay at rest indefinitely until you applied some kind of unbalanced force. You're not going to move. Now pretend like you're in your car for a second. Let's say you're coasting down the highway at a steady 50 miles per hour. Why don't you just stay going 50 miles per hour at a constant velocity? Because if you took your foot off the gas, even if you don't press the brakes, eventually the friction between the tires and the road, the air friction on your car would create an unbalanced force that would bring your constant velocity to rest, right? So maybe a better example is to think of a hockey puck. There's very little friction between the hockey puck and the ice, right? And if that ice could go forever and ever, and if it could be ideal ice that had no friction, and you push that hockey puck, wouldn't it just go forever and ever and ever in the state of motion called constant velocity unless there was some unbalanced force that stopped it, right? So this is the idea behind the first law. We are going to either stay at rest or at a constant velocity until some unbalanced force causes us to either accelerate more, decelerate, or get moving in the first place, right? Cool. So let's go on to looking at a demonstration. I'm going to see if I can pull off a demonstration with this, this video. Let's do one that works 70% of the time. I got a cup, I've got a card, and I've got a quarter. All right, I'm gonna put that quarter here. You can try this at home too, it's kind of fun. Now the question is, if I flick this kind of cardstock piece of paper, what's gonna happen to that quarter? Now if I flick straight up, the quarter is probably gonna bounce off, right? It didn't, right? The quarter stayed there because I didn't flick hard enough. Let's try it again. Nope, that quarter is very heavy. And that's getting into the next thing we're going to write. This quarter has a lot of inertia. So I can't really tilt this thing too well. Can you see the quarter there? Watch what happens next. Quarter's right in the cup, right? You might say, well, yeah, okay, sure, the quarter's in the cup. That's not that cool, but it is cool. It is cool because if you think about it, when I flick the card, there's definitely friction between the quarter and the card once that card tries to move past the quarter. But that friction is not enough to change the state of motion of this quarter. What's the state of motion of this quarter? It's at rest. So again, quarter falls right in. There's not enough of an unbalanced force to change that quarter state of motion. Now the second that card leaves, is gravity enough of a force, a big enough force to change that quarter state of motion? Absolutely, and the quarter fell down into the cup, as you can see right there. All right, so I hope that makes sense. The other classic one of these demonstration of this concept is the whole pulling the tablecloth out from underneath the dinner, the plates, the cups, all that kind of stuff. And my dad tried this one time after his wife had prepared a whole meal for a dinner party, and he tried to pull the tablecloth out from underneath the dishes and everything else. He said, hey, because he was a physics teacher. I don't know if I told you that. He said, hey, honey, you want to see a cool trick? And it totally didn't work. Everything fell off the table, and she was, you can imagine how mad she was, right? Because she had company coming over, and there was now nothing to eat. Physics works, but you have to do it. You have to do it a certain way, especially with these demonstrations. There was too much friction in that situation. Okay. So let's get another term that goes along with this first law. It's called inertia. And you might have heard this term before. This is also called, let's say this, first law is also called the law of inertia. The law of inertia. Literally in the Greek, I believe that inertia or inertia, at least this first part, that root, means lazy. It means lazy. So what is inertia? Well, to define inertia, which I'll do under here, inertia, simply stated, is the laziness of matter. What a technical definition, right? The laziness of matter. If you want a more technical definition, I would say inertia is the property of matter that resists change to state of motion, right? It would resist, me being a big mass, I have a property, and this property is called inertia. And my inertia, which is directly related to how massive I am or how unmassive I am, resists changing state of motion, resists change to state of motion. That means if I'm moving already, I'm going to resist slowing down or speeding up, right? If I'm not moving, I'm going to resist beginning to move. Just like that quarter just resisted beginning to move, even though the card slid right past the surface of the quarter. It said, no, I have inertia, I have a laziness, I want to stay at rest, I don't want to move. Then gravity came along and said, you're going to move. And the quarter said, yes, sir. And it fell right down to the bottom of the cup. Because at that point, the gravity was a big enough force to overcome the quarter's inertia and make it move. So I hope that term makes sense. And when I was first learning physics, I really wanted to pin down inertia as a quantity. Like, inertia must have a variable, right? It must get put into an equation. Well, it kind of is in the equation we're about to discuss in the next law. Inertia is directly related to mass. So you might want to also write that here somewhere. I guess just another statement, right? Inertia is directly related to mass. I'll say is directly proportional to mass. How about that? Meaning the more mass you have, the more inertia you have. The less mass you have, the less inertia you have. So mass kind of is our variable that covers this idea of inertia. All right, good. So that is the first law. That's a kind of a long treatment of it, but I hope that makes sense. Let's get into the second law. We've been talking about an unbalanced force. Well, let's get an equation that discusses that unbalanced force, brings in the idea of mass, and then also brings in the idea of acceleration. So as a mass, you're going to resist changing your state of motion, whether you're moving or you're at rest, right? And however, if a big enough force comes along, an unbalanced force comes along, it's going to move you. And we're talking about now the second law. And the second law is verbally stated as follows. Let me think on this one real quick. Acceleration is directly proportional to force, yet inversely proportional to mass. That is the verbal statement of it, which at first is like, okay, well, that doesn't really sound exciting, and you might not really understand it. So let's build a fake thought experiment and figure this thing out. Let's start by saying, because at the very end of all of this thought experiment, we will state the second law and write it in equation format. The second law is most elegantly stated as an equation, right? So let's get into that thought experiment. So let's look at acceleration versus, let's start with mass. Acceleration versus mass. Okay. So just think about this. It's not hard to think about. You're in your car and you take one friend to the beach, right? And you press your gas pedal down a certain amount, okay? And you accelerate a certain amount, right? Now all of a sudden, you go the next weekend again and your friends caught wind that you're taking trips to the beach, and they're like, why didn't you invite me? You're like, okay, fine, come on, just bring some gas money, right? And so they get in the car, now you got 3 people in your car. You press your gas the same amount, right? You just increased your mass. You got more people in the car, but you push your gas pedal down the same amount. Are you gonna accelerate as fast? What do you think? No, you're not gonna accelerate as fast. It's kind of common sense, right? The more massive something becomes, the less it accelerates with the same given force. And the force in this case is the force of the engine responding to you pressing the gas pedal a certain amount, right? So that's the other important thing with any experiment. You need a independent variable. You need a dependent variable, and I'm telling you which ones are which in this case. You can add or take away the mass, and that will directly affect the acceleration given a constant force. Maybe an easier example is thinking about pushing somebody, right? You go up and you push your little brother with a certain amount of force, he goes flying across the room. You go up to one of your friends who's the same size as you, if not bigger, you push on them and they don't move too much, right? You use the same constant force, but with more mass, there was less acceleration that resulted. And now you might be in a fight with your friend, which is no good. So how do we make a mathematical statement of this? We would say it just like this. we would say A, fish sign, that's that proportionality sign I was talking about in class. A is proportional to the inverse of mass. That is to say that, think about this, if I increase this, that's a denominator, right? If you increase a denominator, what happens to your answer? It decreases it, right? And if you decrease a denominator, meaning you're dividing by less, doesn't that increase your answer? So maybe I'll put here, that would produce that, right? Or I could look at it like this, make the same statement. I'm not saying the statement's any different. I'm just saying if you decrease your mass, your acceleration would increase. What's our conclusion? There's our mathematical conclusion. What's our verbal conclusion? Here it is. Aha! Acceleration is inversely proportional to mass. Cool, right? Good. So that was our first little experiment we wanted to look at. So I'll call that one, I guess, like A, right? That was experiment A. Thought experiment. B, look at, again, acceleration versus force. Versus force, given a constant mass, right? You need two things to be able to vary while a third thing is held constant, given a constant mass. Okay, no problem. In this case, we are going to vary the force, meaning that's the thing you're manipulating in the experiment. You're either adding more or less force. We're going to see how that affects acceleration. That makes that the dependent variable. And we must, to have a good experiment with actual real results, you have to have the third thing being held constant, right? So the mass can't change. Now, I mean, if we're in class, this is like the easiest, best demonstration, right? I usually put an expo pen on the table, and I come over to my expo pen, and I go, and I just knock it with my finger. And of course, the expo pen falls over, right? And the students have no idea this is coming. I love this demonstration. And then I put the expo pen back up. So little force, you got a little bit of speed up, a little acceleration, right? And then I come in and bam, I smack that expo pen, goes flying across the room, breaks the cap, sometimes breaks the pen. And so a big force did what? Created a huge acceleration. Duh, right? This is, I mean, we're doing the easiest thought experiment of the year right here. Small force, small acceleration. Boom, big force. I'm going to do it. I feel inspired. Big acceleration. Pen just flew across the room. It was awesome. Wish you could have been here. All right. So what are we saying mathematically? We are saying that A is directly proportional to force, right? That is to say, if we have a big force, we get a huge acceleration, right? Or a big acceleration, I should say. They're directly proportional. Right? So if you increase your force by 2 times, you get 2 times the acceleration. If you increase your force by 4 times, you get 4 times the acceleration. That's what is meant by direct proportionality, right? And similarly, if we decrease our force by 2 times, meaning we cut the force in half, then we just cut the acceleration in half. If we quarter our force or decrease our force by 4 times, we would decrease our acceleration by 4 times. Counterpoint that up here. If I increase my mass by 2, I decrease my acceleration by half, right? Because isn't that 1 over 2 then, which says A is proportional to a half? So by doubling the mass, you half your acceleration here. Or you could say, if you half your mass, you double your acceleration. Think about putting a little half in here. Please don't write this in. If I put a half in here for mass, what would I do to clear my fraction? I would multiply top and bottom by 2, right? Like that. Those 2's would cancel out. And you can see your acceleration actually is proportional to 2 times what it used to be. If you half your mass, you get twice the acceleration. So you can see how inverse proportionality works versus direct proportionality. What is our verbal statement? Maybe not aha this time. Wow. I don't know. Not really a wow. We already knew this. We knew this by common sense. Wow. Acceleration is directly proportional to force, right? And I'm talking about an unbalanced force here. I am. Okay, so I want to bring these two ideas together, this idea and this idea, into one proportionality statement. So I'll say, see here, combine proportionality statements. No problem, we can do that. I would simply say A proportional to F over M, right? And this would cover the whole thing. I'll let you write that down. The problem here now is I have three things that are able to vary, right? Notice in A and B, we held something constant. So if we let all three things vary, we cannot put an equal sign there, right? That's not going to work. You always need to have something constant. So normally, most of the time, what is the constant out of all three of these things? Normally, the constant in problems when you start seeing example problems is mass. And so I'm going to say here, usually, mass is held constant. Think about it. You say, Susie, Jenny, and Rayana get in a car and travel to the mountains, right? It's still going to be Susie, whoever I said, and Rayana at the end of the trip, right? It's still going to be those three girls at the end of the trip. It's not like one of them got pushed out of the car during the trip to the mountains and the mass varied, right? The mass usually stays the same in a problem. It's not always, but most of the time that's the situation we're dealing with. So usually mass is held constant. And if it is, if we hold it constant, then what we can finally say is A equals F over M. So I'm going to put here, hey, let's hold it constant, meaning it can't change. And if we say that, then we can finally replace our little fish sign with an equal sign. And this is really cool if you think about it. We started with common sense ideas, right? I mean, really common sense ideas, and came up with an equation. We built an equation from scratch, right? And I didn't take a lot of time at the beginning of this lesson because I'm trying to make it quick. It's because I can go on and on with different demonstrations and examples in each one of these laws. But Newton's genius, because he was a genius, right? He co-discovered calculus. There was another guy named Leibniz in Germany who discovered it at the same time, right? Created calculus, right? Newton came up with the universal law of gravitation, which we're going to learn next unit, which was an amazing relationship between any two masses in the known universe, the distance between them, and what the force of gravity really was mathematically based on those ideas. I mean, astonishing that he came up with this relationship, right? He studied alchemy. He was a Renaissance man. He did anything and everything that had to do with mathematics and science. He really did. He even did things where he'd poke his eye. Don't worry, I'm not going to do it, right? With an implement to change the curvature of his lens of his eyeball so that he could start to see the colors diffract as he was looking at things, so that he'd actually see the prism of colors that happened. He would do things like that. He was a weirdo, is what he was. But really, if you ask me what his genius was, is he took common sense ideas like, hey, if something's at rest, it's not going to move unless you push it, right? If something's moving, it's not going to stop unless you try to slow it down. That's the first law. He used these common sense ideas that we just discussed, and he came up with this equation, right? These are things that people had long known, yet he was the one who finally put it all together and said, hey, it's three laws, here they are, boom, 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 they lead into each other. You're welcome, right? You're welcome, science and math community. And that's why I think he was a genius. That's a personal side note. All right, this is not the normal version of this equation. The normal version of this equation is, let's solve this thing for F, and I'm going to add a little thing, so don't freak out here. F net equals mass times acceleration, right? So when I'm talking about this F, the F that we were talking about, it is an unbalanced force. So this F net means, I'll put under here, unbalanced force, just so you understand in context of what we were discussing before. But the way I'm going to refer to this is the sum of all the forces, slash the sum of all the forces acting on an object. So if you've got a dog sled and you got these stupid dogs and one is pulling this way with 50 newtons and one is pulling this way with 100 newtons, but one is pulling this way with 50 newtons, right? You'd have 50 plus 100, which would be 150. This is vector addition, minus 50. So you'd only have 100 newtons that way. That is a sum of the forces. That is an example of what we would say F net is. So the unbalanced force is 100 newtons to the whatever direction we're talking about, right? But to get to that unbalanced force, it was the sum of three different forces, right? And that sum is equal to mass times acceleration. And that's what it means to net something, right? When we talk about our net income, that's after our taxes are taken out by the government and by pensions and by Social Security and different things like that, right? After all of the deductions and even additions, if you made extra hours doing something else, come together, the sum of all that stuff is your net income. Okay, it's another easy example to understand.